Welcome to my channel. This time it's not a project, just some research. I still remember the sensor door project, October 14, 2025, and the LED matrix project, October 21, 2025. Hopefully, the to-do list won't keep getting longer. Haha. Lately, I suddenly got interested in the topic of voice changers and spent some time finding a voice changer project Adafruit made for Halloween. After looking into it more closely, I realized that project is already 12 years old. Even the more recent audio-related projects involving Arduino are at least 5 years old. To be honest, my understanding of music is quite limited. It's not that I can't read sheet music, but rather that sound effects often just register as noise to me. These days, even children's toy keyboards come with tons of sound effects. Not long ago, I had to fix a brand new toy keyboard that was broken right out of the box. The problem was that as soon as it was turned on, it would constantly make loud sound effect noises. The circuit board was faulty, and the most I could do was cut off all the circuits that might trigger sound effects. The most common comment I see about Arduino sound effect projects is that the results aren't great, the processing speed just isn't enough. I thought, how could it possibly be good? It's only running on 5V, after all. Some researchers have done very professional work, directly dealing with digital audio encoding. One project even focused on pitch correction, which can be used for karaoke. If I want to try real-time audio processing, at the very least, I need to understand how to properly connect a speaker and a microphone. And that's what kicked off this research journey, though the topic has ended up going in a rather strange direction. To know whether a microphone is working, I have to be able to hear the sound, so connecting a speaker to the Arduino should be the first step. But how do I actually play sound from an Arduino? Well, that turns into a chicken or the egg kind of problem. While casually browsing chips on AliExpress, I came across something called an MP3 playback module. At first, I didn't think much of it. With streaming platforms always available on smartphones, these seemed like relics of a bygone era. But then it hit me, wait a second, aren't the sound effects on toy keyboards made with this kind of thing? Even though I'm not a fan of sound effects, in theater productions, managing sound cues is basically the same idea. And the large MIDI controller I recently found online, that's pretty much what it's doing too, right? Alright then, let's use that as the audio source. I started focusing my attention on MP3 playback modules. Luckily, I first came across documentation for the DYSV5W MP3 player, along with a video released just a year ago. It seems to be a product similar to the DF player. That suggests DF player is somewhat well known. I found more detailed explanations about it on Amazon. Since Arduino's standard power supply is 5V, I started wondering if it's possible to use a larger speaker. That led me to a video on the topic. At this point, it seems like I've gathered most of the components I'm interested in. I'm planning to use the DYSV5W MP3 player module, but I want to connect a speaker woofer separately through an audio amplifier. A good speaker enclosure is important, but often, you'll find mediocre woofers housed in speakers that look expensive. So I'm thinking of buying a good woofer first and worrying about the enclosure later. Haha. Based on the pin configurations of the DF player and DYSV5W MP3 player, it seems you can connect an audio amplifier without needing a DAC. So, for the hardware connections. DYSV5W MP3 player VCC connected to Arduino 5V. DYSV5W MP3 player GND connected to Arduino GND. DYSV5W MP3 player TXD connected to Arduino TX. DYSV5W MP3 player RXD connected to Arduino RX. DYSV5W MP3 player Busy connected to Arduino D2. DYSV5W MP3 player speaker positive and negative terminals connected to audio amplifier input positive and negative terminals. Audio amplifier output positive and negative terminals connected to speaker positive and negative terminals. Audio amplifier power positive and negative terminals connected to a separate 10V, 24V DC power supply. This setup should allow you to play audio from the MP3 module through an external amplifier and speaker without additional digital to analog conversion. I also downloaded the datasheet for the DYSV5W MP3 player. I learned a lot from the explanation video by Digital Town. In the past, I've written programs that directly used Wii and printer drivers, but this is my first time exploring how Arduino uses hardware driver functions. The TX and RX pins on the DYSV5W MP3 player transmit serial data. If you only need simple on and off control, you can use IO0 to IO7. But since it supports serial control, it opens up many more possibilities. Unfortunately, from here on, I can only imagine how things will work. I don't have the actual hardware yet. Not sure if it will have arrived by the time this video is published. So far, both components still seem fairly inexpensive. It's just that every time I order something, I end up having to wait a long time. From the explanation video by Digital Town, we can see that reading the serial port, TX, TR, does not require the assistance of other libraries. Understanding the encoding method is sufficient. With the current circuit setup, the Arduino can communicate with the DYSV5W MP3 player using the serial object. From the fragmented YouTube video, it appears that the MP3 player's song order is based on the order in which the files were saved, not by file name. If the user deletes a few audio files, the newly added ones won't fill in the missing sequence. When developing games, it's important to pay attention to memory leaks. During gameplay, there are many operations involving adding and removing data. If memory management leads to too many memory leaks, it can result in inefficient use of space where it seems like there's still storage left, but no space is available for new allocations. In other words, as long as there's enough space, new allocations will go into the first available memory block found. However, that spot won't necessarily correspond to the order of removed items. This is likely the reason why the order becomes unpredictable after modifications. Although the documentation lists song numbers up to 256, the TF card supports up to 32 GB. When using serial control, it should be possible to exceed the 256 song limit stated in the technical documentation. According to the definition of specific song in the documentation, using high bits 0xFF and low bits 0xFF theoretically allows for 2 to the power of 16, 65,535, songs. But this can only be confirmed with the actual hardware on hand. I'll also need to prepare 260 audio clips, which is very time-consuming. The datasheet briefly states that the MP3 player uses the UART communication protocol. It's basically made up of two signals, data and clock. I actually found this information through Google. From a software engineering perspective, as long as the sender and receiver agree on a specification, a single session can be used to communicate everything. For example, JSON is a widely used format so long as there are commas, brackets, and key value pairs. The actual lengths of names and values don't matter much. In hardware communication, however, the only thing that can be distinguished is on and off. But how long counts as a single on? If a signal keeps coming in as on, how do we know how many bits were actually sent? That's where the clock becomes important. It helps interpret the timing of the signals. And it must be the same hardware clock on both sides for the communication to work correctly. UART basically transmits 8 bits at a time. In comparison, today's 64-bit computers can transmit 8 times that amount of information in a single operation. Each transmission is defined by a clock cycle. In the real world, things aren't always that precise. Sometimes the receiving side may interpret fewer or more bits within a single clock cycle. How to handle that is up to the receiver's interpretation. This kind of issue is common in network communication. For example, when transmitting video, multiple packets are sent at once to save time. But if even one packet is corrupted or arrives out of order, the entire sequence may be discarded and a retransmission is requested. In hardware, the handling might be simpler. For instance, the receiver might automatically pad missing bits with zeros, or split the data into segments on its own. Compared to Arduino keyboard scanning, which doesn't rely on a clock signal and requires 8 pins just to handle 16 keys, UART incorporates timing, allowing 256 possible options to be transmitted over just 2 pins within a single time frame. That's a bit of a tangent. What I actually want to simulate is a soundboard, which only needs a few simple commands. The following examples use mock codes for demonstration purposes. SM refers to the checksum confirming the end of a command. It is the low byte of the sum of all preceding command bytes. Here are some example serial commands. Set volume to 18. Set mode to play specific track once. Stop playback. Pause playback. Next track. Go back to first track. Play specific track. That's it for the simulation demo. See you in the next video.